Trimester 2, cruising, already up to 5.3 pre-lesson. Back to some graphing. So hope you had fun with all those algebra things. Now we're back to transformations, and you guys have dealt with y equals mx plus b, linear equation. You've dealt with y equals x squared, parabola, and you've also dealt with y equals the absolute value of x, which kind of is like a v. Hopefully you just kind of have that in your head now. You're going to be introduced to a different graph, a different function, and it's y equals the square root of x. So in black here, I'm going to plug some numbers in for x that are easy to figure out. So if I put 1 in for x, the square root of 1 is 1. So I should probably show you how I'm getting these things. So that'd be 1. Put a 4 in, square root of 4, 2. Put a 9 in for x, square root of 9, 3. Now, a quick question. Could I put negative 1 in for x? And the answer is no, because you can't have the square root of negatives. So I know that, well, I should actually put in a 0. I should start with 0. And so 0 works. So there's 4 points that I'm going to graph. So 0, 0, 1, 1, 4-ish, 2-ish, 9-ish, 3-ish. So as you can see, this graph goes up and up and up. It doesn't go up very fast, because if I put in 16, it'd be 4. So I'd go way out here, and I'd be up only 4. So you get the idea that this isn't, let me move this just a little bit. There we go. And so there's y equals the square root of x. Now in red, a new function, y equals the cubic root of x. So again, I pick numbers that are nice to use. Put a 1 in there, and the cubic root of 1 is, oh, I already put it here, 1. Put an 8 in there, cubic root of 8 is 2. See, g of x is right here. So, and then the cubic root of 27 is 3. So if I plot those points, oh, I should also put in 0, I just forgot to. 0, 0, should always start with 0, 0 and see what happens. And then I'm going to go 1, 1. So that's the same point. And then 8, 2, 1, 2, 3, 4, 5, 6, 7, 8 would be like here. 27 would be 3. So you can see this one is flatter than the other one. That's a bad drawing, but you get the idea? So they're very similar. The cubic root of x is a little flatter than the square root of x, but they're very, very similar. So these are going to be called parent functions. So then we're going to manipulate these and see what happens. But before they do that, they kind of give you an interesting problem. It says if f of x equals the square root of 3x, so remember that means this is our parent function. So it's going to be some variation of this black one right here. Make a table of values. And what they're trying to say really is make an easy table of values. Notice I picked numbers that just work. Now they're throwing a little curveball at you. So you got to think a little different. So first of all, if we're looking at square root problems, we have to ask ourselves, the square root of 0, oh, I forgot to say something over here. What if I put a negative 1 in for x on a cubic root problem? Well, the cubic root of a negative 1 is actually negative 1. So this graph actually keeps going. And then if I put in a negative 2, well, no, a negative 8, I plug it in there, that gives me negative 2. So it goes 1, 2, 3, 4, 5, 6, 7, 8. And then I get negative 8, negative 2 would be like that. So this red one would actually kind of go down like this and then kind of like this. So I know the drawing is kind of bad, but that's what would happen if I just kept going. So you can have negative x's in your domain for that one. You may not have negative x's in your domain for that one. Okay, with that being said, move on to this. So I want the square root of 0 because it's nice, it's easy. So what if I just let x be 0 and I plug it in here? So, okay, put a 0 in for x. 3 times 0 is 0. The square root of 0 is 0. Now you got to think backwards. Another perfect square root, the next one is 4. But 3 times some number is 4. Yeah, there is one, but that's kind of a pain. Let's go to the next one, 9. Square root of 9 is perfect. I like it. So what times 3 gives me 9? 3. So I'm going to let x equal 3. And then 3 times 3 is 9. The square root of 9 is 3. So y would be 3. And so I keep going up the ladder, 16. 3 times some fraction is 16, so I'm not going to worry about that one. The next one's 25. 3 doesn't go into 25, nice. The next one's 36. So the square root of 36, I want that. So what does x need to be so that all of this is 36? 12. So 12 times 3 is 36. The square root of 36 is 6. So y is 6. Now, I don't know how far they said make a table, then graph. The book has, they seem to have a habit of picking 4. I'm going to call it good with 3. And then let's go ahead and try to graph this. Let me get rid of this here. And so it says, then graph it. Well, so 0, 0 starts here. By the way, can I have any negative values under here? No. So x can't be negative. So the domain, there's nothing on the graph this way. So it starts with 0, 0, 1, 2, 3, 1, 2, 3, 12, 6, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 6 would be right about there. So it would look something like that. All right. Then they ask for, of this problem, they're saying, okay, what's the domain? What's the range? I told you guys this stuff's not going away. Well, this is how far left does the graph go? Well, it gets to 0. You see that point is 0, 0? It gets to 0. And it gets there. How far right does it go? Forever. How low does it go? Well, if I'm thinking how low does it go, it gets down to 0. How high does it go? It just keeps going up and up and up and then up and up and up. Trick question, are these the same? No, because this is left and right, this is up and down. They just look the same. And then they're going to ask you a question, is this graph increasing or is this decreasing? Remember, we got to move left to right. So we put a guy on the graph, got to move left to right. Looks like he's going up. So that'd be an increasing function. More where that comes from. Here comes your transformations. It says graph g of x equals this. So what you have to think about is, what's my parent function? Well, in this case, y equals the square root of x. And by just memory, you know it looks like this, ish, from the previous example I just showed you. So just get used to that. That's what it is. So now, one thing at a time, what does that do? Well, it's a vertical stretch by 2. So what would that be? It'd go up twice as fast. Now, is that a perfect drawing? No, but it gets the job done. What about that? Well, just so you know, those parentheses don't really mean anything. It's the same thing as that. That would be left 3 units. So I got to take that dotted one and move it left 3 units and try to duplicate it. So I'm going to erase that because we made that progress. And now we just have to move that up 5. 1, 2, 3, 4, 5. Duplicate it, and then that's our final answer. I'm going to make this red and say there. We graphed it. It's the red one. The parent function is right here. So if we had to talk about it, we'd say, hey, we moved the parent function left 3, up 5, and there's a vertical stretch factor of 2. Now, they're going to ask you questions like, how does the domain compare? How do their domains compare? How do their ranges compare? That's just a different way of saying, what's that thing's range or domain? So we'll start with the domain. How far left does it go? 0. How far right? Infinity. How about the range? How low does it go? 0. How high does it go? Infinity. We just got done doing that a few seconds ago on a previous sample problem. Now, how about this one? What's the domain for this one? Remember, that point right there is actually -3, 5. Very important you take note of what that point is. Because, what's the domain? Well, how far left does it go? Well, it gets to -3. How far right does it go? Forever. How about the range? Well, how low does it go? It goes down to 5, and that's as low as this graph gets. How high does it go? It goes up forever. So how do they compare? Well, there, compare them. I mean, I don't know what to say. There's the parent function's domain and range. There's the g of x's domain and range. That's kind of what they want. Okay, I'm going to call this a fun math problem. They want to know what the equation of that graph is. So we're going to call that g of x. And here's just clues. You're like, well, I don't know what it is. And if you got your magnifying glass and think for a second, if we think, hey, wait a minute, let's check that parent function we've been dealing with. And if I said, hey, if x is 1, and I put it in there, and take the square root, y is 1. See that? 1, 1. If I put x is 9, see x is 9, y would be 3. So this is a disguised way of just telling you that this one right here is y equals the square root of x. The information's there, you just have to kind of dig it out. But they want the equation of that one. But now you can say, well, it's a parent function. This is the parent function. So what happened? Well, if you notice, this is 1, 1. This one is 1, 3. What do we do to the y? We multiplied it by 3. Let's see if that's consistent. There's my y. Did we multiply it by 3? Yes. So we're like, aha, there's been a vertical stretch factor of 3, which means our A, so you don't need to worry about B, don't worry about C, don't worry about D. The only thing we're worried about is A. So if the parent function is y equals the square root of x, then g of x has to be 3 times the parent function. So there's a vertical stretch of 3. You can just see it. You got to dig a little, but it's there.